Dear followers, colleagues and friends, welcome back to episode 2 of our 28-ton cement silo design series. In our previous episode, we successfully calculated, modeled and stacked the triple ring cylindrical shell. Today, we are moving downward to engineering one of the most structurally demanding components of the entire system, the bottom conical hopper frustum. I'm Dr. Ali Reza Islamian, with over 12 years of experience as a university professor in mechanical engineering and more than 25 years of hands-on industrial experience in CAD, CFD, finite element simulation, and heavy equipment manufacturing. I'm excited to guide you through this process today. We will bridge the gap between pure mathematical and raw workshop reality. Let's design for manufacturing together. Welcome back to episode 2 of our 28-ton cement silo design series. In our previous episode, we successfully calculated, modeled and stacked our triple ring cylindrical shell. Today, we are taking a massive step downward to engineer one of the most structurally demanding components of the entire system, the bottom conical hopper. Follow along closely and let's design for manufacturing together. Before opening SolidWorks, let's establish our physical parameters. The bottom hopper functions as a massive collection funnel, bearing the full static weight of the cement column and immense dynamic friction forces during discharge. To safely handle these loads over years of continuous outdoor service, we are increasing our structural plate thickness from the 5 mm used in the shell up to a robust 6 mm plate specifications, utilizing reliable ASTM A36 structural carbon steel. The geometry of our hopper forms a truncated cone, technically known as a frustum. The large upper diameter is fixed at exactly 2,500 mm to line up perfectly with our cylindrical shell. The lower discharge opening tapers down to a small diameter of precisely 300 mm to interface with the standard industrial butterfly valves. To ensure an exact 60 degrees flue angle, our vertical height is calculated to be precisely 1,905.2 mm. Let's verify this critical 60-degree angle mathematically. If we take the radial difference between our large and small diameters, we get a horizontal base measurement of 1,100 mm. By applying trigonometry, the tangent of 60 degree multiplied by our base gives us an exact vertical height requirement of 1,905.2 mm. This sharp 60-degree slope is the gold standard for cement handling, creating an aggressive mass flow layout that prevents powder stagnation. As engineers designing for manufacturing, we must compute our material yield and weight metrics early. The net surface area of this specific frustum shape measures 9.67 square meter. Fabricated from 6 mm structural steel with a density of 7,850 kilograms per cubic meter, the net weight of the finished cone stands at 453.6 kilograms. This structural mass must be securely supported by our upcoming leg assembly. While modeling a solid cone in CAD takes only a few seconds, preparing it for the cutting table requires a deep understanding of flat pattern development. When a three-dimensional frustum is unrolled into a flat sheet, it forms a curved sector of a circle bounded by an inner radius and outer radius and a specific sweeping development angle. Let's look at the math behind unrolling this shape. Based on simple trigonometry, we calculate the slant length of the folded frustum as 300 and 2,200 mm. These slants determine the radii of our unfolded flat pattern. The inner radius of our unfolded frustum is equal to the small slant of 300 mm, while the outer radius is the summation of both slants, 2,200 mm plus 300 mm, giving us an outer radius of precisely 2,500 mm. This slide shows a brilliant mathematical shortcut for unfolding cement silo hoppers, valid only for 60 degrees angle, of course. At exactly 60 degrees, the slant length is twice the radius. This creates a beautiful simple relationship. The unfolded sheet is always a perfect semi-annular shape, spanning exactly 180 degrees. Furthermore, the inner radius of this flat pattern always equals the small diameter, and the outer radius always equals the large diameter of your hopper. When we analyze the footprint of this unrolled flat sheet, we find its width spans nearly 4,800 mm. Because standard heavy steel plates are typically available in widths of 1,500 mm or 2,000 mm, we cannot cut this hopper from a single sheet. To solve this, we can either split the flat pattern into two equal halves with two seams, or weld two structural plate filaments side by side to create a wide canvas for a single shot cut. In this project, we will implement the filament-based method. Two steel plates are welded side by side to create our raw cutting sheet. In our SolidWorks assembly, we position the larger 5100 mm by 1500 mm plate fixed at the origin. We then made the second 4100 mm plate side by side with a precise 1.5 mm root gap for welding. Aligning their top and front planes guarantees the absolute flatness. To verify our dimensions, we overlaid the semi-annular flat pattern directly onto the welded plate assembly in SolidWorks. By mating the flat faces and aligning their central planes, we confirmed that our raw plates fully cover the required cutting area. Allocating ASTM A36 steel reveals that the raw plates weighed 650 kg, while the cut frustum is 456 kg. Leaving roughly 200 kg recyclable scrap metal after cutting. We also explored a Mosaic nesting layout to minimize waste, reducing the scrap by 100 kg. However, this saving comes at a high cost. It replaces our clean layout with multiple smaller plates requiring excessive cutting, alignment, and welding. Thus, it creates perpendicular weld lines with dangerous T-joints oriented along high-stress directions. This multi-semi layout also risks uneven bending and wrinkling during the rolling process. Ultimately, the simple two-plate filament method remains the superior choice. Beyond labor, there is a serious metallurgical risk. Hot-rolled steel plates possess a directional grain structure from the rolling mill. When we align and weld two large parallel filaments, their microcrystalline behavior remains homogeneous. In contrast, rotating smaller plates in a mosaic pattern results in mismatching grain directions. This causes uneven stretching during cone rolling and leading to flat spots, structural wrinkles, and severe fatigue weak points under cyclic hopper loads. For optimal flow, we require 4 22 mm holes placed 700 mm up the slant height. Cutting these holes while the plate is flat on a CNC plasma table yields perfect clean edges. However, the subsequent cone rolling process will slightly deform and shrink these holes into minor ovals. To compensate for this mechanical distortion, we recommended cutting the flat holes slightly oversized at 25 mm or drilling them to final size after rolling. To bend a flat curved sheet into a perfect three-dimensional cone, standard cylindrical rolling machines are inadequate. We must use a specialized heavy-duty for-roll plate bender equipped with a mechanical conical rolling attachment. This device acts as a hard stop shoe that drags on the smaller inner radius, slowing it down while forcing the wider outer radius to pass through the roller at a faster speed. This yields a uniform, perfect taper shape. This slide shows our manufacturing drawing, including the 1.5 mm root gap and 2 mm root length for the initial plate assembly. Crucially, the welding seams connecting our raw plate filaments must be ground perfectly flush on both sides before rolling. Any protruding weld beads will cause the plates to slip or bind in the heavy cone rollers. This creates severe geometric defects and flattening errors in the finished hopper. A major challenge in heavy plate rolling is the flat end defect. Because the plate edges lose contact with the bending rolls at the start and end of the cycle. The machine cannot curve the absolute boundaries. This leaves straight, unbent profiles at the joints. To prevent this, we added 75 mm flat lead margin to both ends of our raw plate cuts. After rolling, we trimmed these flat zones away to achieve perfect roundness. Now let's build this geometry step by step using native SolidWorks sheet metal tools. We open a new part file and generate a reference plane with a precise vertical offset of 1905.2 mm relative to our top plane. These planes lock in our 60-degree slope. Next, we will sketch our driving cycle directly onto these two distinct levels, laying the foundation for our sheet metal feature. We sketch a 2500 mm circle on the top plane and a 300 circle on the new plane. Here is a mandatory rule for SolidWorks sheet metal parts. Sketch loops cannot be completely closed or the software will reject flat pattern calculations. We use the Split Entities tool to introduce a tiny 1.5 mm gap in both profiles, aligning them perfectly on the same vertical seam axis. Next, we navigate to the sheet metal toolbar and select the Lofted-Bend command. We select both open circle profiles from our design space. In the settings, we choose the formed option to guarantee a completely smooth continuous skin rather than a faceted bent press brake finish. We input our sheet thickness of 6 mm and ensures the offset direction points inward. This maintains our critical 2500 mm outer limit. Because this 6 mm hopper handles high pressure, proper joint preparations is a vital safety requirement. For all structural seams, we implement a 60-degree included single V-groove butt weld. We grind a 30-degree bevel onto each joining edge. This leaves a precise 2 mm flat root land. Combined with a 1.5 mm assembly root gap, the configuration absorbs the thermal energy of our welding torch without risking edge blowout. To prevent material bridging, we are integrating a 4-array fluidization system spaced at 90-degree intervals. The 22 mm holes sit 700 mm up the slant face. In SolidWorks, we model this by generating a reference plane tangent to the cone, sketching a circle, and using a sheet metal normal cut. A circular pattern then duplicates it 4 times over 360 degrees. When we unsuppress the flat pattern in SolidWorks, you might notice it deviates slightly from a mathematically perfect semi-annular arc. This is not a software bug. Standard math assumes a zero-thickness surface, whereas SolidWorks factors in real-world material stretching and compression using the K-factor. This deforms the 2D output slightly. Let's open a discussion for our audience. In your workshops, do you rely strictly on cat flat pattern exports, or do you prefer laying out heavy cones using manual geometric formulas? Let us know in the comments. Another common CAD challenge is applying weld bevels and chamfers to the top and bottom circular openings of a sheet metal frustum. Because the faces are curved, applying standard chamfer features often results in distorted edge geometries and errors during flattening. We want to hear from you. How do your design teams handle weld prep chamfers and rolled conical parts in SolidWorks? Do you model them as 3D sweeps, for example, or leave them as notes on the 2D manufacturing drawings? Please share your workflow below. Our 6mm hopper is now fully modeled. When mating it to our main assembly, we rotate its vertical seam far away from the shell's weld lines to eliminate concentrated stress zones. Our total structure mass model so far stands at 1,964 kilograms. Thank you for watching. In our next episode, we will climb to the top to design the structural roof deck. Remember to like, subscribe, and we will see you there. To support your own projects, I'm making all our design assets available to you. If you would like to receive the SolidWorks CAD files, 3D step or XD model extracts, the PDF manufacturing drawings, or even the PowerPoint presentation slides from today's episode, it is very simple to get them. Just subscribe to the channel and leave a comment below with the corresponding keyword: CAD for the models, PDF for the drawings, or PPT for the presentation. Thank you so much for your valuable time and outstanding support. If you find the engineering insights in this video helpful, please don't forget to leave a like, subscribe to the channel, and share your thoughts in the comments. I will see you in episode 3, where we will design the upper roof deck together.